Alright, so in a previous video, I mentioned that 0 and 1 basically represent something or all of something and nothing. Right? 1 representing the something, 0 representing the nothing. These are, ordinary enough sort of intuitions here. Nothing, obviously, that's what 0 is, and something. Alright, so as far as integers go, this is... I disagree that it's even a valid category of numbers. It's certainly not like a natural class. It's not a category that you would come across normally, in a normal sort of sense. There are ways you can construct it for sure. So what the numbers are, like 74, 87, whatever, that kind of thing. What the numbers are is basically, you just take these guys and you just keep adding them together. Just give more and more and more of something, and more and more and more of nothing. A whole bunch more of nothing, whatever, doesn't really do anything. So the only thing that ends up counting, the only thing, right? That's where we get the word counting. The only thing that ends up counting is the somethings. So a whole bunch of ones stuck together can give you 7 or 412 or 27 trillion and 8, right? Doesn't matter how many of these guys you have, because they're not going to change the value. You can add zeros all day long, and you're not going to get that. You're not going to get anything different. It's interesting that, as far as I can tell, this pair of numbers isn't recognized as a category. It doesn't have a name. All of the other non-zero integers, that would be the non-negatives. All of the other non-negative integers, right? I don't know what I'm saying. All of the other non-negative integers can be grouped into primes and composites, right? So primes are the things that there's a couple ways you can analyze it. You can analyze it with addition, you can analyze it with multiplication, but the more common way is with multiplication. They're the numbers that you can't really divide anything into other than 1. So as far as multiplying, really this is the only thing. This and the number that you end up with are the only things that go into it evenly. I think even in Euclid's Elements, he mentions something like that along those lines. It's confusing and it's in weird old Greek, so whatever. But yeah, he mentions something along those lines. So you get the primes like 2, 3, 5, 7, whatever, and then the gaps between those are the composites. Because by definition, if the primes is the class of numbers that can't be made of, they don't have other factors other than 1 in itself, well, any gap in there is going to be something that has more factors than just 1 in itself. Like 4 is made up of 2 times 2 as well as 1 times 4, things like that. So you get these guys, 2, 3, 5, 7, yada yada, and then the gaps, 4, 6, 8, 9, 10, yada yada yada. So these are the primes. These are the composites. And insofar as that goes, I don't really have a problem with that. It is interesting, though, as far as I can find, these two, which are very, very fundamental to mathematics, You can build up everything really from just understanding these guys. They, as a category, don't seem to have a name, as far as I can tell. So I have elected to give them a name. I call them the existentials. And if you dispute that name, if you have issues with it, I don't really give a fuck. I don't know who you are. Whatever. You're free to, you know, you're free to speak a different language from me, as far as this goes. Right? A torch and a flashlight, ultimately, they're the same thing at the end of the day. The thing to understand is this is what I have called that. That's, as far as I know, nobody else has named these. I'm calling this because they refer to the fundamental aspect of existence. 0 is when nothing exists. 1 is when something exists. And these guys are made up of multiple things existing, right? It's a collection of, it's these guys happening over and over and over again. So there's really nothing fundamental about these guys. They're built from these, and you can actually see this in number systems. You can actually see it even in our number system. You know, like Chinese. 1, 2, 3. Well, really what we did, the 1 we just turned it, we just rotated it 90 degrees. The 2 is just cursive. And so is the 3. It's just bam, 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 bam. 2, 2. 1, 1. Right? Even in our number system today, it's still, you know, like in school, you know, I hear a lot from teachers kind of looking down on, you know, like Roman numerals. 1, as if they understand it correctly. But it's the same sort of thing, right? Roman numerals, 1, 2, 3, 4, hello. Four, and then a special one for 5, 6, 7, 8, 9, and then we got 2 5s stuck together. That's 10, 11, 12, 13, 14, 15, and then we just, you know, in order to mark, so say we want to abbreviate this, well, if we wanted to say 14, it's going to be that 1 right before this 5, but this 5 is right after this this 10, so it's going to be abbreviated thusly. We've gone 10, and then we go to the 1 right before the 5. That's how Roman numerals work. They explain it with all these other rules. I don't. Whatever, this is what the rules actually are. I don't know. I don't know why they're doing that. Ultimately, it comes from a tally system, just like our Arabic numerals do. Or, you know, even, you know, Mayan, 1, 2, 3, 4, 5, 6. So here they're doing it, you know, but with the hand, with all the fingers of a hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. 10 is 2 hands. 20 is 1 person because you have feet. 10 is kind of coming into play. Kind of like Iron Age, late Bronze Age, Europe. It's really coming into play, I think, for the primary reason that you get people wearing shoes a lot. Particularly, so this is partially speculation, but it's pretty well attested. The the Bronze Age collapse and that period in between, there was a lot of sort of peasant revolts going on, and you get a lot of kingdoms, well-established kingdoms, being overthrown. The old power pretty much ends up being the suppressed, and the previous suppressed become now the oppressors. So those would have been people who had a pedigree of their history was they would have been peasants formerly, so they wouldn't have been as fully educated, which is basically why Rome had to completely reinvent mathematics. Greeks sort of kind of started over, and you can actually see that in Greek literature and whatnot. They talk about it. They tell you directly that that's what happened. It's just I don't know why nobody wants to acknowledge that that's what they're saying. They're saying it very very plainly, and you can see it. Like you go from you have these number systems that make sense. They are very well designed. They are based often on multiples of 12. So you get 60 and 30 and 36 and 12 and 24s and these sorts of things happening, right? So you have 12 hours of sunshine during a day, 24 hours in a day total, so a pair of 12s. Yeah, it's kind of convenient for this system that there's just over 360 days in a year, but that's not really where it's coming from. There's 60 minutes in an hour. 60 is really, really handy because it is divisible by 1, 2, 3, 4, 5, 6, and then 10. So we miss a few, but 9 and 8 go in there pretty conveniently. So there's very little we miss. There's a really good reason to be doing this, to be going with something like base 60 or base 12, and that's what the educated people did before the Bronze Age collapse. But after the Bronze Age collapse, most of Eurasia moves to a base 10 system, and you often hear today that that's because we have 10 fingers. Well, it is not actually anything to do with that. Yes, it is true that we have 10 fingers, and the European tradition is to count the fingers, and that's how you get the 10. But the fact that you're not counting the toes, the fact that you're counting the finger itself instead of the spaces between the fingers, where you could either get 4 or 6 very easily, or you can do something like Australian Aborigines, where you count around the fingers and then you come up the arm and then you come down around the head and down the other arm, and you get, there's a lot of ways to count numbers on the human body. Base 10 is in no way, the one that makes the most sense. It's just the one that caught on in Eurasia. And it caught on in Eurasia really only after the Bronze Age collapse. And I think this is important to understand about mathematics. It's kind of a fundamental thing about mathematics. It feels like a history lesson, I'm sure, but we tend to look at mathematics where everything is base 10. That's really, really important somehow. And no, it's really not. You have, basically everybody in the Americas doing everything in base 20. From the Mayans in southern central Mexico and Guatemala, that area, up to the Aleuts in Alaska, the Inuktitut and whatnot, the Cherokee, everybody in North America, not everybody, but the most widespread system in the Americas is base 20. Base 10 is exceedingly rare in the Americas. Things like base 4 or base 8, something like that, is quite common, particularly in the Southwest. There's a lot of variety in possibilities, and there are some languages and cultures in the Americas that don't even appear to have had counting really at all. So, yeah. Trying to say, oh, it's base 10, we use 10 because we have 10 fingers, that's not really wrong, but it's not true either. And this is something that I see messed up quite a lot. You get told that it's because we have 10 fingers, and it's really, fundamentally, it's not. It's not, because what about your toes? Your toes are perfectly good to count on, and lots of people around the world, including in Eurasia, prior to the Bronze Age collapse, used base 20 as well. There is Georgian and Basque, which are belong to language families. I think also, I could be misremembering this, but I think also Uralic languages, like Finnish and Estonian, natively use base 20, but they've all kind of come around to base 10. Yeah, they're from language systems or language families that are not Indo-European, even though they're in sort of the European continent. So they're sort of these little islands that survived whatever happened and whatever caused the expansion of Indo-European. I have my own opinions about how that happened, and they differ from mainstream views, but one way or another, it happened. Indo-European languages spread over the continent and more or less wiped out everything else, and you end up with these little pockets like Basque and Georgian, and and they have these remnants. They do things like Basque directly will use base 20 for a lot of things. And I think Georgian, it's a little bit less obvious, but it's definitely there. So you get these things. Ultimately, though, what numbers are, it's just a collection of ones crammed together. Although importantly, the only way I can recognize the difference between these ones is the space in between, the zero in between. So the zeros are also quite critically important. Kind of a proper way, I think, to frame how, like what a number is, what 3 is, or something like that, is kind of like we did with the exponents, which was iterated multiplication, but we had a starting point. We had a definite starting point. What we can do is we can look at, numbers as being the same sort of thing. So 4, for instance. Well, you could look at it as 1 plus 1 plus 1 plus 1. So 4 ones added together. And this is kind of like he's saying the exponents is like 3 to the 4th power is 4 threes multiplied together. That's fine, but it works. But here, the thing that we're doing, we're only doing it 3 times. So it's kind of weird that we have 4 objects and there's 3 things happening. What we really should want is something like this, where we start with nothing and we add something 4 times. So again, we have our starting point, and then we have our action that we are repeating this many times. So that's what 4 is. We start with nothing and we add 1 4 times. Right? And this is why, because this is kind of, as far as the existentials are concerned, this is what integers basically are, because you can't have you can't have something between nothing and something. Right? You could have half a loaf of bread, but really half a loaf of bread is something. It's 1 half a loaf of bread. Or even the numerator in the half, it's telling you that it's one thing. It's 1 half. So, basically this is what's happening. Alright, so we kind of end up in this weird sort of system of thinking about numbers, I think. We don't think about it this way. We're not familiar with looking at it this way. But we see when we're taught multiplication, for instance, we do kind of see it this way, and it's kind of the only place we see it this way that I, at least that I was taught, or the curriculum that I see as a math teacher that I see anymore. Um, something like 2 times 3. We'll think of that as, okay, so we've got 3 2s, or 2 3s. Either way, doesn't really matter. What we should actually do is, should be a 1 in there. No, wait. These are pluses. These are pluses. I'm stupid. I'm doing exponents when I should be doing... Yeah, there should be a nothing in there. And then we're adding. Should be a nothing right there. And we're adding. Okay, so we're sort of familiar with seeing multiplication treated this way. Usually you don't get the 0 added in. But technically, if it's really only the 2 times 3, then there's nothing else. So this is actually part of it. This is important. It's an important part of it. And when you start counting, say I want to count off 4 things, you're going to find an edge. You're going to find a 0 point. And from that point, you're going to start counting. So every time you count, you actually do start at 0. You find an edge, and that's your 0 point, and then you start counting off. Right, like if we're going to count the lines on this paper, it would be really strange to start in the middle. You're going to start at the top, or you're going to start at the bottom. It's really, really weird to start in the middle. Oi. Okay. Lots of fun in this video. Okay. So, and this actually comes into play with some operations that you're extraordinarily familiar with. Like division, for instance. The fact that this 0 is here is actually of critical importance to properly understanding division. So, this will ultimately... Hello. So what happens when I attach my camera to a cylinder? It loops around. It doesn't really want to sit on that. Okay. Numerically, this is 6, of course. So, kind of the opposite version of multiplication is division. So if I did something like 6 divided by 2, what that actually means is I'm going to take 6 and repeatedly subtract 2 until I get to 0, and then I'm going to count how many steps I made. So, getting back to the multiplication, that 0 right there, that's our starting point. That's our 0th step. This plus 2 is our first one. This plus 2 is our second one. This plus 2 is our third one. So we get 3 times 2, or 2 times 3, however you want to read it. Over here we get 0, 1, 2, same sort of thing. 0, 1, 2, same sort of thing. And what we're going to be doing with the division is we're going to be taking this number, subtracting off, whichever one, in this case it's going to be this guy, until we get to 0, and then we're going to count how many steps we did. So unless I frame multiplication this way, it's extremely confusing what in the hell division is. Right, so I get 6 minus 2 is 4. That's step 1. And then we get 4 minus 2 is 2. That's step 2. And then we get 2 minus 2 is 0. That tells us to stop. And we stopped on step 3. So 6 divided by 2 equals 3. That's what division actually is. We always want to terminate on the 0. If we cannot cleanly terminate on the 0, then the sort of fragment, the piece that's left over, we call that the remainder. The distance between um, where the last complete step was able to finish and 0 is the remainder. So we always, with division, we absolutely always end at 0. And if division is properly the opposite of multiplication, that means that multiplication always starts with 0. It has to. And if multiplication is starting with 0, addition also is going to start with 0. And exponentiation is the one where we have to begin with something existing. Here we're beginning with a lack of existence. We're beginning with a blank. Exponentiation begins with existence. So it starts with a 1. Its first step is 1. And then every next version up from that, like tetration and whatever, they are always going to actually start with a 1 as well. So addition, well, not even addition. Numbers, multiplication, which is the iterated application of numbers. So notice here, really, addition isn't even a function, isn't even an operation. It isn't a basic thing in the way that I'm presenting mathematics here. We have the existentials, 0 and 1. From that, we get the numbers. From that, we get multiplication. And then kind of a bastard form of multiplication would be your ordinary addition. So multiplication and addition are sort of the same thing. It's really sort of the same thing going on. We're just kind of cramming together some numbers. And if all the numbers happen to be the same, we call that multiplication. If they're not necessarily the same, we call that addition. That's the only difference. And then iterated multiplication, we call that exponentiation. So now we get into some interesting questions here. Namely, what is an integer? So I keep running into the claim, and to be fair, it's never like cited like where this came from. So yeah, like a lot of things in school, I think it's just somebody said something once and whatever, and it wasn't even necessarily wrong the way it was said originally, but people didn't really pay attention to what was being said, and they sort of interpreted it and whatever, turned into sort of garbage. But I hear a lot when I'm looking at math curriculum, and they're talking about integers. I often see it referenced, not so much in the newest textbooks, but there was when I went through school and kind of when I started teaching math, I definitely saw it a lot. Claims that the integers was a category of numbers that the Greeks used. This actually is not true, because integers, as we have them now, were actually defined in the 1800s, and they include 0 and the negatives, which were both sort of controversial points for the Greeks. So, yeah, definitely they were not. You also run into problems. So integers are, essentially the numbers you can count to, right? Those are these guys. And the negative versions of that. I have some reservations about the negatives, because I don't think they're properly numbers unto themselves. The negative, it really acts in basically every regard as a unit, right? It's not really a part of the number. It's a part of the thing that you're counting. And this does have the implication that positives really have the same trait, that positive numbers aren't actually numbers themselves either. So 4 and positive 4, in my view, are actually different from each other. So you can take the absolute value of positive 4, but really you can't take the absolute value of 4. The absolute value of positive 4 is 4, but then the absolute value of 4 doesn't actually make sense because it doesn't have a sign. Once you've taken the absolute value, what you've done is you've removed that directionality, and that's really what it is. It's, say positive goes that way, well, that means negative goes this way, and the negative of the negative goes that way. So it's like, we applied the unit twice, and it undid itself, sort of a thing. And neither of those are traits of the number. They're a unit, right? Like one dog and one computer, they're both one of something, right? But you wouldn't say that one dog is a number that is different from one computer, right? 1 is the number. In the same way, 4 is different from positive 4 and different from negative 4. And negative 4 and positive 4, in a sense, are actually the same sort of thing. This is a subtle point, but I think it's worth at least kind of bearing in mind. Because playing with it this way, it's really all I'm doing is I'm just pulling these out, I'm just getting more and more and more of these things to get the numbers. That doesn't lend itself to a model of subtraction. The only way I can get subtraction is once I have one of these guys and I pull some stuff off. Now it's sort of like a meta-analysis of what I did over here. It's a deeper level. It's not as fundamental, right? So it's at the same level as addition, which is kind of in this space here. Like if we're like most basic is up here, this is a little bit more developed, a little bit more. We've done things here. This is just how things are. You either have nothing or something. Here, we're counting off how many somethings you have. Addition and subtraction are one step beyond this, where we've established how you can count the somethings you have, and now we can deal with relative counts in various ways. Right, like if I have 7 things and I remove 3, what does that give me? Sort of a thing. Or if I have 12 things and I add 80, what does that give me? That's living in this space. That's sort of multiplication is sort of the special case for that. And addition is the generic case, multiplication is the special case. So in a sense, these two, kind of like a rectangle and a square, multiplication and addition are really the same thing. And similarly, subtraction and division are also the same thing in that sense. And then, so really our stages, our levels are existence, the existentials, numbers, addition, multiplication, multiplication being sort of a special case of addition, and subtraction, division being special cases, or being, kind of their parallels, where we can reverse it. And then the next level is the exponents. So this ends up giving us some interesting things, because now it's really, really strange to say, to have this category that is the positives and negatives of the numbers. All right, it is weird. It is kind of how it's framed. Like they'll say, yeah, these are the natural numbers or something, but they'll often leave out 0 in that category. It's not really, or the whole numbers, or whatever. Like okay, that's fine. And then the integers, it's those and their negatives. Like, yeah, okay, I guess that kind of makes sense as a category. But we do run into a problem. We run into a problem when we get to fractions um, with these guys. So the rational numbers, right? So those are. It would be really nice if we could say that it is the rationals are it's the set the set of things that you get when you take this category that we just established, and you just divide it by other members of this category that we just established. The problem is you can't do that because you can't divide by zero. Division by zero is not mathematics. So when you try to divide by zero, you get paradoxes. Some really, really interesting ones. And yeah, I'll show in a second why division by zero is undefined. It's not there isn't a value. It's not infinity. It's not anything. You can't know what it is. Um, but yeah, we have this next sort of basic category of numbers that we're taught in school, the rational numbers. But you can't compose them simply from the categories that we've already been given, because the categories that we've been given, they grow. Really, the first category is the numbers that you, when you're counting, the numbers that you would say, right? So when I'm counting off 4, I don't say 0. I never say 0. I find an edge, and that's the act of recognizing 0. That, right? The way that I handle the 0 is by finding the edge and to count from, and then I say these steps, right? That's that's what I that's what I'm saying is these guys. I don't say the 0. So you kind of have this intuitive sense that 0 isn't really a part of this, isn't a part of the numbers. So that's sort of where that category comes from. But then the next category up includes the 0. And then we include the negatives, right? So, we just add on we recognize this has a direction, and we could go the other direction. Okay, that's fine. But then we want to take the fractions between those. But we've already included 0 in there. And now we have the problem that we have to kick it out in a certain spot. And this feels really broken to me. It's like, whoa, your hierarchy that you've established here is bullshit. Like, you're trying to, I'm pretty sure what it is you're trying to sort of appeal to, like, what you think little kids can understand the best. It's like, okay, the numbers that we say, 1, 2, 3, 4, 5, yeah, that's a category. And then, okay, yeah, but really, you can also have nothing, and that's 0. So it's 0, 1, 2, 3, 4. Okay, but yeah, I can take things away, and that, or you can owe me something, and that's a negative number, so we can have that. Okay, but then we can also cut things into into pieces, right? We can take this loaf of bread and divide it amongst 4 people, or we can eat it over the course of 6 days, or right. So we're either dividing it by 4 or we're dividing it by 6, something like that. So how much bread do you get each day if you're dividing it 6 days? Right, you get that sort of a thing. The problem is we've built up our sense of numbers to very, very early include 0. And then suddenly, after we've spent a lot of time on this, we have encountered a category where we would like to be able to use the categories we already established. But because we were unwise in the way we established our categories all along, we're unable to actually explain what the hell rational numbers are. If instead we kind of came back to, okay, it can be any of these guys that you would say divided by each other. and their negatives. And we also know about 0. Now you've established the category that is what we recognize as rational numbers. It's in sort of an equally awkward way because I had to say and 0. But it is a more elegant way because I didn't have to say, oh, and by the way, down here in the denominator, not 0. It's covered. It's covered because the things we can divide together are these guys. The somethings. You can only divide something by something. You can't divide nothing. And you can't compose something of nothings. So really, 0 cannot be a numerator or a denominator. So fundamentally, the rational numbers are nonsense because the way we formulate it, we allow 0 to be a numerator, and we should not do that because you cannot take nothing and cut it up. Just as much as you cannot take something and compose it of nothings. This something cannot be built out of absolutely nothing. It has to be built out of something. And this nothing cannot be cut up some set number of times. It doesn't make any sense. Right? So, conventionally, this is a problem, 7 divided by 0. That's not math. Right? You can't do that. But we do allow the opposite, 0 divided by 7. We're like, oh, well, just define it as 0 divided by anything as itself. You can do that, that's fine. The problem, though, is you can't actually take nothing and divide it by something. You can't break it up. What this means, what one interpretation of this means, is we took something, we cut it into 7 pieces, and then took none of those pieces. Well, you could have just told me that we don't have any. You didn't have to go into all that detail about the 7s. Whereas this... Oops, where's my camera? There we go. Whereas this actually means something. The 3 I can't get rid of. This 7 I can absolutely get rid of. The 7 doesn't tell me jack shit. I don't care. It's not part of it. It's not doing anything. Over here, the 0 is breaking it. Over here, the 7 is not contributing anything. This 7 not contributing anything basically means that this isn't math either. This isn't math any more than this is. We can get this to make more sense than we can get this to make sense. But really, it's really the same exact relationship, just represented in 2 different ways, right? You can even see this in ratios, right? So if the blue team scored 7 points and the red team scored 0 points, well, the red team scored 0 points and the blue team scored 7 points. It's the same exact relationship. So why would one be bad and one be good? That doesn't make sense. Also, when we try to talk about rational numbers, when we try to talk about fractions, using just these guys, the odd man out is the 0. Guess what? That's the correct interpretation. The odd man out should be the 0. The 0 is the thing that doesn't work here. 0 is the thing that broke it. 0 shouldn't be a part of your rational numbers. Okay. So now I mentioned that, we can't know what the value of a division by 0 is. We can actually show that pretty easily. So say I've got something like y equals x plus 2. Something very, very simple, right? We can graph this just, very, very easily. So there's your y-axis, there's your x-axis. Where we're hitting the y-axis is at 2. All right, so it's 45-degree angle that we're coming up. Okay, no problems, right? Okay, let's take this and let's play with it a little bit. So I'm going to modify this a little bit. What if we said this is y equals 1 times x plus 2? That's exactly the same thing, right? Because x, 1x, same thing. An apple, 1 apple, literally the same thing. And is just a different pronunciation of the number 1. Okay, so an x, 1x, same thing. No problems. This and this both graph the same thing. What happens though if I modify the way that we say this 1, right? So anything divided by itself is 1. So what if I say that R1 is actually x plus a divided by x plus a? Well, this should be 1. This should always be 1, because anything divided by itself is 1, right? That should never cause me a problem. Okay. So this should give me the same graph as this. Problem, though, is what happens when x is negative a? Whatever a is, when x is the negative of it, I'm going to get a division by 0. And we don't know how to do that. We don't know how to divide by 0. In the top, I'll also get a 0. So I'll get a 0 divided by 0. But because there's a division by 0, I don't know how to do it. So we can't say that 0 divided by 0 is 1. We can't use that shortcut, because anything divided by 0 is not even math. Also, what this value should look like is sort of dependent on what a is. So I can't really know what division by 0 really should be producing. Because this x is actually also being divided by 0, right? So this whole term right here can be any value. It can have, right? It can have any x position. It could be 47, it could be negative 6, it could be whatever. It's just going to be the negative of this. But I'm dividing by 0, which means division by 0 can yield any number. Absolutely any number. And 0 divided by 0 is not 1. We can't make that claim. So here I have a numerator that I can't divide because it's a 0, and I have a denominator that I can't divide by because it's a 0. We recognize that the denominator 0 is a problem culturally. The numerator 0, we kind of just found workarounds, and we're like, whatever, it's good enough, we'll just say it's 0. It makes sense. There's ways you can get that to make sense. But yeah, you can show with this whole thing, really, it's x squared plus ax over x plus a. Sometimes this part is going to be 0. So I have a division of some random, it could be anything. This should evaluate to anything. But we're dividing by 0, so so say a is negative 1, right? So when x is 1, we would get a 0 over here, right? So what we should get on the top would be x is 1, right? Yeah, and that's negative 1, so we get 1 minus 1, 0, divided by 0. Okay? That will give us a whole. So we end up with, wherever it is, we always end up with a hole somewhere in our graph because we can't actually evaluate it at that point. We can know perfectly well what it should be, but we can't do it because there's a division by 0. And if I just modify the equation a little bit, I could get it to behave in any other way that I wanted. And we can always introduce a division by 0 anywhere in a graph very, very easily. So, and the graph can be anywhere at any height. It can have any value. So we can demonstrate really, really quickly, really, really easily that division by 0 could be any number. It can be anything. So that's bad. Division by 0 is bad. Division of 0 is also a problem. There's also some weird things that happen with numbers that you conventionally get told, right? Like 1 plus 1 is 2. Problem with that is we can make it not true very, very easily. So let's do, 17. Let's make 1 and 1 be 17 instead of 2. Well, this is pretty easy. This is very, 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 very easy. What we can do is we just find denominators that add up to 17. And when we multiply those denominators together, they will be the denominator. And there you go. So 1/16 plus 1 over 1 is 17/16, which I think you can see very easily because this would be 16/16. Add 1, you get 17. That is absolutely true. We took 1 something, we added another 1 something, and we got 17 something else's. And this is actually how the world really works, because if you take an apple and you add an orange, you don't get 2 oranges. You don't get 2 apples. You get 2 pieces of fruit. You had to do a unit conversion in order to get it to make sense. Right? Here I have 2 somethings. That's true. I do have 2 somethings. So the sense that 1 plus 1 should be 2 is fine. But here I also have 2 somethings. 7 plus 8. Those are 2 somethings. That didn't give me 2. That gave me 15. So here I have 1 thing plus another thing giving me a third thing. 1 plus 1 gave me 15 in this case. Right. This way of recognizing how the numbers work is not taught at all. And it's quite shocking to me because not understanding this, not recognizing this, sort of makes the 1 plus 1 equals 2 thing that everybody takes completely for granted not make any goddamn sense. So really there's a lot going on here that it's like a really basic level. Like we're just talking about what does 0 mean? What does 1 mean? What are the numbers? How does division work? That's really all we're doing here. And at every step, we've found something that is conventionally missing. I find this pretty deeply disturbing when I'm trying to teach math, because there is a complete lack of foundational understanding of how anything works. Like it's fine to not have a full grasp on all of this, but it's really hard to explain to somebody how division really works without showing them how multiplication actually works. And it's really hard to set up this version of multiplication without really understanding how the numbers work. And it's really hard to set up how this works without understanding that this pair, 0 and 1, is quite fundamental. And it's really hard to say that this is quite fundamental when it doesn't even have a fucking name. This category doesn't have a name. So at every step, there's problems.